Okay, lesson 58, forces. We will be able to describe the attributes of a force. What I mean by that is what makes up a force. What is a force? How do we measure it? So on and so forth. Both the book decides to go about this in a weird way. I would normally do a very small introduction to forces and then go straight into Newton's first law, Newton's second law, and Newton's third law. The book spends actually a fair bit more time explaining the basics of forces and talks about force diagrams. Now, I'm not sure if I'm going to get time to talk about force diagrams today, but we will talk about force diagrams very soon. But I thought what I would do first is I would just talk about the basics of forces, just so that we can all cover it and we're all on the same page. Last time I spoke to you guys and I taught you something was with regards to projectile motion and kinematics. So that's understanding kinematics, of course, understanding the equations that go to make up how we understand distance and displacement velocity and how they're all linked together. And then what we did is, the other reason I taught you guys projectile motion, so you guys could get a bit of an idea of, hey, we've got a vertical velocity that's affected by gravity, and that the other thing as well to understand was, when you throw something up, it also then has to come back down. And so the time it takes to get up, the final velocity upwards is 0. When it gets to the top, it then starts falling. So that's one of the trick, is that at the top of the arc, the upwards velocity will be 0. The trick is to know how long does it take to get to that top? How far up does it go before it gets to that top? And that can be calculated using this equation or using V equals U plus AT. Next, we're going to look at forces. And the first thing we're going to do is going to start off at the very beginning, a definition of force. You guys have seen this definition time and time again, but I'm throwing it up there in a sec. First, I'm going to talk about what is mechanics, because you remember I said that all of Newton's laws are split up into dynamics and mechanics. Mechanics is just split up into dynamics and kinematics. So this is us moving into dynamics. So first thing Newton said is, one of the big things Isaac Newton is known for, he's known for a lot of amazing things. What was he known for? He was the very first person to show that light could be split into individual wavelengths of color. He was the first person to help invent calculus. He calculated pi to a very high amount. What he's essentially known for mostly nowadays is his 3 laws of motion, which he wrote down in the Principia Mathematica. What he wrote in this is he wrote down what those 3 laws are. But in order to firstly understand what the 3 laws of motion and the 3 laws of forces are, we really need to break down what a force means. So what is a force? A force is a push or pull on an object. Okay? Plain and simple. I like this because it's a pretty easy definition. This is the same sort of definition I'll give to you. 7s, 9s, 10s, no matter what. But because we're a bit, what it can do is it can change its motion. It can change the motion of an object or its shape or size. Now in year 7, when I've taught this multiple times, what I always do is I say, there are 6 things a force can do. It can, start something moving. It can stop something moving. It can speed something up. It can slow something down. It can change the shape of something, or it can change the direction it's moving. But to be honest with you, all of those are the same as just saying it can change its motion. You can accelerate it. You can make it speed up from 0 or from 1 or from 2 to like 10, or you can slow it down. And also, acceleration, which means change in velocity, if you change your direction, this is something that haven't really spoken about a lot. And this more comes up in year 12 as a bit of a mind sort of blow. is that velocity has a direction. So if you change the direction of your velocity, then you're also changing your velocity. That means that what a force can do is it can change your motion no matter what. Force, like, is a vector quantity. It has a direction. You can only push or pull in a direction. Pushing and pulling, by the way, can be considered the same force, just in different directions. A pull is like a negative push, if you want to think about it like that. And of course, force is measured in newtons, or N. 1 Newton is about the amount of force needed to pick up an apple. That's usually what the classic definition is there. But, you know, if you don't like that definition, then, you know, then you can think of your own. It's like 10 newtons is the amount of force needed to pick up a bottle of milk. Whatever you want. I'm going to leave this up for a second, and then I'm going to change the slide. Not long enough for me to grab a bite of toast. Okay. Next. Okay, there are two types of forces. Contact force. The contact force is where a force where the force is left. Contact force is a force where the force is applied by something touching it. Can someone give me an example of a contact force in chat or out loud? Up to you guys. A push. Yeah. Punch in the face. Someone else said privately. Good answer. Either of those two. Friction is a contact force. Good job, Richard. That's actually one of the harder ones. Yeah, it's actually weird because a lot of people like remember the non-contact forces, which are the harder ones, but usually the contact ones. So yeah, that's why I put this picture of a cricket bat hitting a ball. Like, this here is a contact force. The bat is pushing against the ball. So yeah, I would say a push is definitely, I would say an example of it is an impact force. I might call that. What I want you guys to do is, whoopsies, I want you guys to write down some example. I actually think friction is probably a better example because you guys will be doing a lot of stuff with friction. But I'm just going to write an impact force because that's just kind of what I've got a picture here of. I don't want, like you might say, what about push? It's like, I don't really want to use the word push. The reason I don't want to use the word push is because it doesn't necessarily mean, like if I say, oh, if I push something with a magnet, you know, that's not necessarily a push force. So anyway, whatever. Non-contact force is applied, but nothing touches it. So what's an example of a non-contact force, people? There are like two major ones. Magnetic is definitely one. There are three major ones actually. Magnetic, gravity, and the last one, no one ever knows. The last one is electrostatic. That's like when you get an electric shock when you rub your feet against something. Static electricity. Static electricity, so that's static electricity that holds like a balloon up against the wall. That's not the same as magnetic force. It's a whole brand new force. Well, it's not brand new, but yeah. Now, oopsies. Before I move on, just really quickly, I wanted to flesh this out here because you guys, it says it in the book, and I wanted to throw it out there. Last topic we talked about the 4 fundamental forces. So gravity, electromagnetic, Gravitational, electromagnetic, weak and strong forces. Now, those are the fundamental forces. But the problem that we have here is, and this is a problem that we're going to cover a fair bit, is that these forces are not very useful for everyday life. As I've mentioned to you before, we don't see these strong and weak force in everyday life. They act over a too short a distance, and so we only really see gravity and electromagnetism interact. And even then, when we see them interact, they're very much like they work together sometimes, and sometimes they act in weird ways. So therefore, even though those are the fundamental forces, what we usually do is we refer to other types of force. So, for example, friction, which was just talked about before. Friction is not a fundamental force, but we will refer to friction as a force because even though friction would be made up of gravity and electromagnetic and other forces, we're just going to refer to it as its own force. So, first, let's talk about, all right, in chat, quick guess. Does anyone know what this is? Or out loud, up to you guys. Who wants to have a guess what this is? I'm not going to move on until I get a guess. What does it look like, people? What is this? Come on. Something that measures force. Hyperbolic time chamber. I like both of those answers. Good guesses. It is neither of those things. But I'm glad that you guys had a guess. This is the kilogram. You guys might have thought, oh, hold on, he misspoke. He must mean a kilogram. It's like, no, I did not misspeak. This is the kilogram. In France, well, actually, that's a lie. This is not the kilogram. This is a copy of the kilogram. In France, deep inside a vault, there is a single, I think it's a rod of platinum iridium. It's a platinum iridium rod that has a mass that is 1 kilogram. I say that it is 1 kilogram because what it's used for is for setting other devices what a kilogram is. What does that mean? Okay, so if you've got a kitchen scale, right, or you've got a bathroom scale, and it says, you jump on the bathroom scale, let's say it weighs 8, it tells you, hey, you weigh 82 kilos. You gotta say, well, okay, how does it know what a kilo is? Well, it was probably calibrated by some kind of device at the factory. So, its dial said, when you read this, that's what 1 kilogram is. So that's how it works. And then you might say, well, okay, well, that device that's at the factory that calibrates what kilogram is, it itself needs to be calibrated. It needs to know exactly what 1 kilogram is. So and all of those devices are probably calibrated at the central office of that company. But even that central office calibration needs to be calibrated by something else. So it probably gets calibrated by something else. But eventually you need to calibrate it by something that 100% is a kilogram. And that's exactly what this metal rod is. Now, the interesting thing is that about 2 years ago, they changed the definition of a kilogram. It is no longer the mass of this rod. It is now the mass, I think it's like the mass of like 12 million silicon atoms or something like that. But yeah, that's what it was originally used for, is for measuring the mass, is so that we had a definition of what it was. We had the definitions of all things like that. We had the measure of a meter was a length of rod that was stored in like a vault in France, I think. And yeah, there's like lots of other ones as well that were stored. Anyway, but not the point. The point that I wanted to talk about, and the reason I've got this is because I wanted to talk about that. What does it mean to be 1 kilogram? And that leads to the question to what causes gravity. Okay, so this is gravitational force, the very first one that I wanted to talk about. Gravity is caused by mass. Okay, all objects with mass pull on each other with mass. So gravity is a pull force. Okay, so you can actually define a lot of the forces as either pull or push or both. So what gravity does is it pulls on it. If you've got mass, then you will pull on other objects that also have mass. Okay, if electrons have mass, so they will pull on other electrons with a tiny amount of mass. Of course, the repulsive forces will outweigh the gravitational forces, but still they will pull each other a little bit. If I keep going down, gravity is also a non-contact force. Yeah, you don't need to be in touch with gravity in order for it to move something. So gravity is a classic example of a non-contact force. There are actually a fair bit of issues with gravity being a non-contact force back in when gravity was first being discovered, because they didn't like the idea that a force wouldn't have a that you couldn't measure it, it didn't have anything touching it. But I'm not going to explain that. So here's a quick question for you guys: what object has the most mass? Here's a random question. This is the question that I usually give people. The object on Earth that has that's how I'm changing it. What object on Earth has the most mass? The Earth, exactly. So what object on Earth has the most mass? The Earth. The Earth has the most mass, which is why we are pulled down. So basics here, people, but it's actually going to be important here. Gravity attracts us to the Earth because the Earth has the most mass. And this might make you think that the force of gravity is strong, but we've already talked about how weak the force of gravity is. In fact, as I said, you can overcome the force of gravity by jumping in the air. You can overcome one of the fundamental forces just by jumping. It shows you how strong the electromagnetic force is compared to the gravitational force. Now, here's the thing. If mass creates gravity, that means you're being pulled closer now to all the other people, and usually I would do this in a classroom, so that's why it doesn't make sense. You're being pulled closer to everything within your arm's reach. You look around you, and you can see like a coffee cup, a phone, a marker. All those things are being pulled towards you, but it's a very, very small mass. It's a very, very small force. I do want to point out, and this is the part where people get confused, that means that you, even though the Earth is pulling you down, you are still pulling on the Earth. The Earth is still, for all its importance, is still an object that has a mass. So you can apply a force to the Earth just by pushing on it. So you can still apply a force to it. It will probably won't do anything because it's very, very small, but you can still apply a force to it. These things on the left here about changing distance and stuff like that, we're actually going to cover that when we talk about Newton's second law. Of course, the Earth is not the most massive thing in the solar system. That'd be the Sun. The Sun holds the planets in orbit because of gravity. We all get attracted to the Sun because it is the most massive object in the solar system. The reason that we don't fall into the Sun is because we're spinning around the Sun at a fast enough speed that we are falling into the Sun, but we change our direction so often that we don't actually ever end up in there. Plus, There are other gravitational pulls, like we're getting a small pull towards Jupiter and so on and so forth. So they also balance out. So that's gravity, right? Oh, not quite. We've one little thing left of gravity. What time have we got here? We've got about 10 minutes left. Let's do gravity, then we'll bash out friction probably, and then that'll probably end. So what's the difference between weight and mass? This is something that we talk about a lot in year 7, and then a lot in year 10 as well. So hopefully you guys don't need a refresher. It's but just in case you do, weight is a force. So we call it the weight force. It has a direction. Weight force is caused by the gravitational pull. So your weight force, 980 newtons or whatever it is the force that you experience on the planet. Now, mass is a measure of the amount of matter inside an object. Okay, it doesn't change depending on gravity. So your mass on Earth will be 100 kilograms. If you go to the sun, if you go to the moon, then your mass will still be 100 kilograms because it's a measure of the amount of stuff inside of you. Now, or a measure of the amount of matter inside of you. The amount of matter is governed by, the amount of atoms, which is governed by the amount of protons and neutrons. So that's why your mass doesn't change. You're not changing the amount of protons and neutrons inside of you as you go from the Earth to the moon. But your weight does change because the gravity on the moon is a lot less than the gravity on the Earth because the moon has a lot lower mass. So your weight is a lot less. You feel a lot less heavy, and that's why you can jump so high on the moon. Now, the equation, by the way, that links the weight force to the mass of the object by G, the gravitational acceleration, which for Earth is 9.8. So this here is the formula that we're going to use. This is, of course, for those of you, many of you guys will see, this is Newton's second law. All I've done is instead of using A, I've replaced with G, and G happens to be 9.8 meters per second squared. Oh crap, I shouldn't try this. Meters per second squared. Now, I will let you, you don't really need to know this, but just a heads up, it's not 9.8 everywhere on Earth. That actually changes depending on where you are on the Earth. And of course, it's not going to be 9.8 on the moon. I think it's only about, you can actually calculate it. You could take this value, divide it by 100, and that'll tell you what it is. So it looks like it's about 1.6, which is, I think, about a sixth of the gravity of the Earth. I think it's like, the Mars is a third of the gravity of Earth, whereas the moon is a sixth of the gravity of Earth. I only got that from reading a fiction book about this stuff, which is kind of interesting. Yeah. So that's just the thing. One last thing I will mention about weight is that, and I read this recently in your textbook, they actually said, we don't use the word weight. And I'm going to try and avoid the use of the word weight as well. Because they said, and even this, they said, weight is never used in the VCAA curriculum. Like it will never be, you'll never see the word weight put on an exam. The reason that they don't put the word weight on an exam is because they said there were two reasons. One, because weight is actually a little bit more complex than just this formula. The weight formula also, I think, takes into effect other things like essentially like what type of shape your body is and stuff like that. So therefore, and what type of how it works with the center of mass. So they don't usually use the word weight because it's more complex than just what we do. Also, the other reason they don't use the word weight is because there's a lot of confusion. If you go to someone, oh my God, I'm overweight, that doesn't mean that your force that you're putting down on Earth is larger than it should be. It means that you have more mass than you should have. And that's because of a colloquial term. Like the common way we refer to weight is, how much do you weigh? And when you say how much do you weigh, you want to know how many kilograms. You don't want to know how many newtons. So therefore, even though in physics we draw a definition between weight and mass, for future reference, we're probably never going to use the word weight. We're probably only going to use the word the gravitational force instead of using the word weight, just so you know. All right, we've got about 5 minutes left. Let's power through friction is the last. Okay, I don't think I can get through all of friction, but I'm going to try. I'm going to start, at least it's going to start friction for the last 5 minutes. Friction. Now, friction is a force created when two surfaces are in contact. Okay, it only slows or stops an object from moving. Now, this is actually pretty important here. A lot of this stuff is important here. The first part is that one, we know now that the force of friction is a contact force. Okay, it has to involve two things touching. You can't have a frictional force without two things touching. The other thing that's actually important is it only slows or stops things from moving. You can't use the frictional force to speed you up. So one time I saw I've seen questions where it's like, oh, you're traveling 20 meters per second to the right, you experience a frictional force to the left of 5 newtons or something. Now you might say, oh, cool. That means if I start going to the left, I can use this frictional force to speed up. But that's not how it works. If you turn your little bike around and you start traveling to the left, suddenly the frictional force will then start moving to the right, because the frictional force always slows you down. It always opposes your motion. You can never use it to speed up. Air resistance is like friction, but it's caused by objects moving through the air. And you can also have like resistance through objects moving through liquid, like water resistance. But that's obviously water resistance is a bit of a different topic, but still, any time where you're trying to move through a fluid, whether it be air or move two objects past each other, you will have some form of friction. Now on these two pictures on the left, they've got two examples of brakes. The first one is a brake that's on a bike. These two arms here squeeze in and squeeze onto this piece of metal here. You can see this pad is squeezing onto this piece of metal, which will create friction. This was a, if you're, for me, born in the 90s, this is what pretty much everyone got for Christmas 1995. Well, you know, except I think our family got one. It was a red one. Maybe you guys still have them. Maybe they're buried somewhere in your garage. This was a Razor scooter. If you were cool, you would have one of these. And this at the back here was the brake. What you would do is you would push down on this, and that would create friction. The problem is that it made this bar really, really hot. And of course, when were you most likely to be using this Razor scooter if it's Christmas time? You probably didn't have shoes on. I remember being on a Boxing Day, was riding around on one of these scooters, did not have shoes on, was going down a hill, tried to put the brakes on, burned my foot trying to put the brakes on, and ended up jumping off the scooter onto like some grass because I was just like, I can't stop this thing. I'm going to go down and crash and die. So yeah, and then I never used the scooter again. So just, yeah, friction causes heat, because ultimately all that energy that you are removing because you are slowing the object down needs to go somewhere. The energy goes into increasing the internal energy of the metal, or heating it up, making it hot. We're going to talk a little more about energy in a week or two, so be ready for that. All right, that brings us to the end of this lesson. So we've just all done this lesson, talked a bit about what force is. We didn't actually do very much. we did a bit about what force is. We did a bit about what gravity is, what causes gravity. And then we finished up with a quick chat about friction. Next time I see you guys, we're going to go through what factors cause friction and then how we can reduce friction. So just two little things. And then what we'll do is we'll move on to the next two, which is tension and compression and tension. Yeah, compression and tension, I think, and the normal force. I remember the normal force. So that's what we're going to do next time. I will see you guys then.